function of bounded variation. So we define function of bounded variation as follows. So we say that let f of x be defined on this closed interval AB, and if P is any partition on that AB, and if there exists a positive number M such that this expression is less than or equal to M, and this expression here is just simply this. That is, we have explained this under Riemann-Stieltjes integral. So this expression is just this. So if this happens for all partition P in this, then we say that this f of s is a function of bounded variation. So when it happens like that, we say that f of s is a function of bounded variation. Another close definition of bounded variation is a total variation, which we normally use in place of this definition. So it is given as follows. So we define it like this. Let f be a real value function defined on a closed and bounded interval days, and if P is any partition on that AB, you have known what partition is, then this expression V of A comma B, or we write it like this, which is equal to supremum of this one here, which is this, the supremum of absolute value of delta FR. So this expression is called total variation of f. So if you have this type of expression, we call it total variation. And in case whereby this expression, if it is finite, then we say that f is of bounded variation. So that's it here. If f, that is this, if this v, this total variation, if you have found it and we see that it's finite, that is, it is not infinity, that is, the value we get is not an infinity value, then we say that f is of bounded variation. So that is another close definition of bounded. If you find the total variation and we see that the total variation, the answer is finite, it's a finite number, then we say that that function is of bounded variation. So let's consider the following theorems. So the first theorem we consider is this: a bounded monotonic function f is a function of bounded variation. So let's prove it. So we have been told that this function f is a bounded monotonic function, that is a monotonic function. If a function is monotonic, definitely it is bounded. So we start by the statement that is a bounded monotonic function. So let's consider a monotonic increasing function. So this is it here. We want to consider a monotonic increasing function f on interval a comma b, and you know what we mean by that. You know, for instance, let's say f is s squared. I gave something like this before. Let's say this is the interval. So that is for all, if you put s here, if s is 1, this is 1. If s is 5, this is 5 squared, which is 25. You see that this one is less than this. So we'll see that it is increasing for all these values that moves from 1 to 5. If you put them here, the value will be increasing. So that means I can say that f of 1 will be less than or equal to s, will be less than or equal to f of 5. So if a function is monotonic, it must be like this. That is, if I put f is equal to y, it must be less than or equal to this last one. So we now say that consider a monotonic increasing function of f. So since that f is monotonic increasing, then by definition we know that f of a, this first one, will be less than f of s, will be less than f of b. So which I can just write in another form, which I can just write as this one. If I can decide to write it as f of sr minus 1 is less than or equal to f of x is less than or equal to f of SR. So that is, if instead of AB we are considering, because we want to put it in summation form. So let's take note of this. Now we only got this from definition of monotonic increasing function. So to now show that it's of bounded variation, we need to find the total variation. So we need to find the total variation, this. So we need to find this. So whether it is finite or not. Now let us now find v of fa comma b. Let's find this. R runs from 1 to n. This is the fr, and that will just give me summation r runs from 1. You know that this one is f of sr minus f of sr minus 1. This is what we have. But since f is monotonic increasing, definitely this f of sr will be greater than f of r. We can see it, that this one will be greater than this. So without any stress, you see that this will be greater than this. So let me put the supremum there. Now, but because we know the reason why this absolute value is there is that we don't know whether this will be greater than this or this will be greater than this. We don't know, so that we can neglect the negative for absolute value. But because we have been told that f is monotonic increasing, definitely this will be greater than this. In that case, I can take away this absolute value. I can turn it to bracket, because we know that since f is monotonic increasing, this will always be greater than this. So I can turn it to bracket. Now if you put f is equal to 1, what we are going to have is if you put r to be 1, what we are going to have is f of s1 minus f of s0. So plus the next one will be f of s2 minus f of s1. It will be going like that until it gets to when r is n, f of n minus f of s n minus 1. So from this, you all observe that this and this will be gone. In fact, all of them will be gone. The only thing that will be left will be f of sn minus f of s0, which is same thing as I don't need to put this because this is constant. It is constant. So which I can write as f of b minus f of a. So you see that this thing is finite. See, because we have been said that the function is bounded in this interval. So definitely it will be defined in the interval. F of a and f of b will be defined in that interval. So this is finite. Since this expression is finite, therefore f is of bounded variation, and that completes the proof. Let's consider another theorem. So we have another theorem here. A continuous function on AB is not necessarily of bounded variation on this. So let's prove it. So we start by saying, since we start from this continuous function, this statement. So we say that since f of s is continuous on AB, then it must be uniformly continuous on that. So we have said it before. So since f is continuous on this, then it must be uniformly continuous on this. So then we call by definition of uniform continuous. For every epsilon is greater than 0, there exists theta greater than 0, such that absolute value of f of a minus absolute value of f of b is less than epsilon for all A minus B is less than delta. So which I can just write as absolute value of f of b minus absolute value of f of a is less than epsilon. Is inside absolute value, so I can rewrite it like this. It's inside absolute value. I can rewrite this one to is inside absolute value. For all b minus a is less than delta. Now let us write it as this will be SR. This is SR minus 1 is less than epsilon. For all SR minus 1 is less than delta. Now from this list, let's take the summation of both sides. R runs from 1 to n. Summation R runs from 1 to n epsilon. For all, don't forget that this thing is just delta SR is less than delta. This is capital letter, that is small letter. So let's put supremum to both sides. Supremum this f of SR minus 1 is less than, don't forget that epsilon there is a constant, so we have summation 1. Summation 1 we just get, sorry, I'm putting supremum to both sides. Summation SR, this is epsilon. Summation ordinary 1 is just n for all these. Don't forget that we have proven this under Riemann integral to be limit n tends to infinity. This is epsilon n. So as n tends to infinity, this will be infinity. So you see that this expression is not finite. Though we have less than here, I can write this thing as v of f a b. So this is less than or equal to infinity, because here we don't know the kind of value it may give, but although we got less than infinity, so it may be it may be of bounded variation, it may not be of bounded variation, because you can see we have infinity here. So that shows that not every continuous function that is of bounded variation. So that proves the theorem. Let's consider another theorem. So, but before the theorem, we'll consider the following definition. So this is the definition here: Lipschitz function. A function f of s is said to be Lipschitz on this interval if for every epsilon is greater than z, there exists delta greater than z, such that f of a minus f of b is less than m into this. You should know that this is less than epsilon. So from this we can get our delta here. Now this is, if this occurs, we'll say that that function is said to be Lipschitz. So we now have this theorem 3. We say that every Lipschitz function is of bounded variation. Let's say on AB. So let's prove it. So since f is Lipschitz, then by definition, that will be definition of Lipschitz. By definition of Lipschitz, this will happen, which we have written out. We know that we can also write it as f of b minus f of a is less than or equal to m into b minus a. So let us write it in terms of SR. This is f of SR minus f of SR minus 1 is less than equal to m into SR minus SR minus 1. So let's put supremum and summation to both sides to write the definition of total variation. This will be less than or equal to m supremum of r runs from 1 to n. We know that this one is just delta SR. This one. Now, don't forget that this one is positive. This thing is greater than is always greater than or equal to 0. So in that case, I can decide to remove this will be m. I can decide to remove the absolute value in that delta because it is positive. So from this place now, we know this one to be b minus a. By the time we substitute these things, we know this one to be b minus a, or if you write it to be delta SR to be b minus a over n. Summation n is 1. It's n already. Summation 1 is n, so they will cancel each other. So we know this to be b minus a. So what we have shown is that VFAB, the total variation, is less than or equal to m into b minus a, which is finite. This thing is finite. So since it is finite, so we can now say that therefore f is of bounded variation. So we have just shown that every Lipschitz function is of bounded variation. Let's consider another theorem. So we have another important theorem here. If the derivative of f of x, that is this f prime, exists and is bounded on this AB, then f is of bounded f of s. This f is of bounded variation. So we start by this. Since f prime of s exists, so that is f of s is differentiable on a comma b. If they say that f prime exists, simply means f of s is differentiable on this. And also bounded. Then by definition of bounded function, there exists a number. By definition of bounded function, we are familiar with this. There exists a number m such that absolute value of f prime of s, remember, is less than or equal to m. This is definition of bounded function, but it's not f that is bounded here. What they said is bounded is f prime of s, that it exists and is bounded. So let's keep that as equation 1. Let's keep it. And don't forget that they said f of s is differentiable, that is f exists. F is differentiable. Also, if f is differentiable at a comma b, then it must be continuous by theory of continuity and differentiability. So where we started is this: f prime of s exists and bounded. That if f prime of s exists simply means it's differentiable and it's bounded. If it is bounded, you are told that it's bounded, so we call this definition of bounded function. So we kept it. Now we go back to this statement that the function is differentiable on this thing. So definitely by theory of continuity and differentiability, every differentiable function is also continuous. So, and if you have these two, then we can apply mean value theorem. So then by mean value theorem, we say that Mean value theorem says that if f of x is differentiable in a closed interval and is continuous in an open interval, then there exists point C belonging to this such that f prime of C is equal to f of B minus f of A over B minus A. That is what mean value theorem says. Now let's write this thing like this. Instead of C, let us put TR there. Instead of B, let us put SR. Instead of A, let's put SR minus 1 over SR minus 1. But don't forget that T belongs to SR minus 1 comma SR from this place. Our TR belongs to that. So from this place now, we can have this thing to be f prime of TR times this one. If you cross multiply, it to be delta SR, which is same thing as f of SR minus f of SR minus 1. Now, this, from this list, let's take absolute value of both sides. I will put summation after we have taken the absolute value. So let's take the summation and absolute value of both sides like that. This absolute value of TR, absolute value of delta SR. This is equal to summation R runs from 1 to n, absolute value of SR minus absolute value minus SR minus 1, then absolute value. Now, where we can rewrite it like as this, and don't forget the whole of this, I've written it like this, and this is equal to, I wrote this first. This expression is just this thing. Now, by equation 1 here, we have been told that f prime is bounded, so definitely this will happen. So by equation 1, f prime is less than, absolute value of f prime is less than or equal to m. So what we are saying is that this will be less than or equal to this is absolute value of f prime. I can put m there, which is r runs from 1 to n. It remains absolute value of delta SR, but this is positive. I can remove the absolute value. So this will just be m into, we have known that this one is just the whole of this is b minus a. So this expression, what we have shown is that this expression delta FR is equal to, is less than or equal to m. So this is finite, and it also goes by definition of bounded variation. So we can now conclude that therefore f of s is of bounded variation. Now the following, we take an example now. That example will tell us, we throw more light on the fact that not every continuous function that is of bounded variation. In that case, take the following example. So we have the question here. Consider this function, this given function. We show that this function is continuous on this, but not of bounded variation on the same interval. Now we start for the continuity. So for the continuity, we make use of the definition of continuous function. So we start by saying if for every epsilon is greater than 0, there exists delta greater than 0, such that absolute value of f of x minus absolute value of f of s naught is less than epsilon for all x minus S naught is less than delta. Our S naught here is 0. So our f of s, this is our f of s here. So our f of s is this, which is s cos pi over 2x minus f of 0. But f of 0 by definition, you can see that is when s is 0, f of s is 0. F of 0 by definition is 0. It's less than epsilon for all s minus. This is 0, it's less than delta. But we know that this is absolute value of x, absolute value of cos pi over 2s is less than epsilon. For all this absolute value of this is less than this. But we know that this one is 1. Absolute value of cos theta, we know that that one is 1. So this will just be absolute value of s is less than epsilon. For all absolute value of s is less than delta. If we compare both sides, you will see that delta is equal to epsilon. So we have found delta, so which depend on epsilon. Since we have found delta, this which is equal to epsilon, and that delta, that means the delta depends on epsilon, and we conclude that f is continuous on this. Suppose we are unable to find delta, then we say that it's not continuous. So let us now check for bounded variation. So for bounded variation, let's consider, we need to consider a partition. So let's consider this partition. Let's consider partition on AB on 0, 1 as follows. Now, what are we considering? What will be the partition? So the partition of this one is special. So we consider this partition, this, like that, up till it gets to, let's say, 1 over 4, 1 over 3, 1 over 2, and 1. At least this is 0 and 1. Now we consider this partition. After considering the partition, then we get our subinterval from it. So we cannot find the total variation. That is total variation 0, 1, and that will give me r runs from 1 to n, absolute value of SR minus absolute value of this minus 1. Now this thing will become, when s is 1, when s is 1, so we'll be using this thing. This is f of 1 minus f of half plus absolute value of f of half minus f of 1 over 3, like that. You pair them, plus f of 1 over 3 minus f of 1 over 4. It will be going like that. It will get to f of 1 over 2n minus 1 minus f of 1 over 2n. So that is the meaning of this, plus f of 1 over 2n minus f of 0. So that will be the last one. F of 1. So we know our f of x. We know that our f of x to be x cos pi over 2s. So we only need to be substituting all these things there. Anywhere we see s, we put it as 1 and all those things. This will be cos pi over 2 minus. So let me write them out. So put s to be, anywhere we say put all these things there. So we are going to have the following. So I have written everything out. So we'll be putting s to be all these numbers. So but we know that cos 0. In fact, generally, let's take note of this. We know that cos n pi over 2 will be equal to 0 if n is odd number. And ordinary cos n pi, this will be minus 1 raised to power n. So for all n, but for this one, when we have n pi over 2, if n is odd, then it will be 0. So as you can see here, this will be 0. Cos pi is minus 1. So this will just be half. This one is half. Plus, this is minus half, minus 0. This one, this is cos 3 pi, you can see, is 0. Plus, this one too is 0. Minus 1 over 4. This is minus 1 raised to power 2. This is still 1. So it will be going like that until it gets to, this is n pi over 2. 2n minus 1 is an odd number. So this will just be 0 minus cos n pi is minus 1 raised to power n. This is minus 1 raised to power n plus this is 1 over 2n. This one is minus 1 raised to power n. This is 0. So from this place, this is half. Absolute value of half is half. This is also half. This one is 1 over 4. The next one will have been 1 over 4. It will have been double like that. This is 1 over 2n. Minus 1 raised to power n in absolute value is positive. This one too is positive. You see that this one too, you can see that it's double. This is minus 1 raised to power this. So this will just be 1 over 1. This is this. Plus 1 over 4 plus 1 over 4 is 1 over 2. The next one will have been this. Up till the last one here will have been 1 over n. This thing is just harmonic number. I will know that harmonic number diverges. So what we have seen there, what we have seen in that place is that v of f comma a comma b is infinite. Hence, f is not of bounded variation. So we have seen that that function is continuous, but it's not of bounded variation. Let's consider another example. So this is the second example. Show that this function is continuous, but not of bounded variation. So it will proceed. You proceed the way we did for example 1. I only give you hints for the partition. So we'll consider the following partition. So use this partition to obtain the total variation. So you see that the answer is not valid. It's not finite. So it will not be of bounded variation. That will be left as an exercise. So we still consider this theorem. This theorem says if f is of bounded variation on this, then f is bounded on that. So we only start by the statement that since f is of bounded variation, then we call the definition. So we say that since f is of bounded variation, then there exists m such that this is less than or equal to n. So that is by definition of bounded variation. So now let's consider this. Let's consider this f of x, which is let's consider this f of x to be f of x, let's say plus, I can say f of let me just use any constant. Let's say f of n minus f of n. You know that f of n minus f, whatever we have written here is the same thing as this. So which is the same thing as f of x minus f of n plus f of n. So if we put absolute value to both sides, you will see that this will be absolute value of f of x minus f of n. To separate this absolute value, if I want to separate that, I must put less than or equal to by triangular inequality. So that is using triangular inequality. If I want to separate them into absolute value, I'll put less than or equal to there. Now, if you take summation to both sides, summation r runs from 1 to n, absolute value of x, which is less than summation this minus f of n. This is summation this, absolute value of f of n. So this is independent of n. Don't let me use n because of this n that we are using. Let me use k here now. Let me use k so that you not look the same. So this is independent of this R. It's independent of R. So in that case, I can write it as f of s is less than. Don't forget that this is just variation function. F of s comma a. This is just f of s comma a. This is independent of R. So I can still write it as absolute value of f of n. But we know that this thing is just this. So this will be less than or equal to m. Let's assume that the whole of this is okay. Let's put it there, but it's constant, sure. So let me write the whole of this to be p c. So we can now have that absolute value of z f of s is less than or equal to p. So when we have this type of relationship, so you see that this thing means f is bounded, and that completes the proof. So let's consider this example. He said we should show that this function is a function of bounded variation on this interval 0 to pi over 2. We are asked to find this total variation. So it's very easy to show. We only need to make use of our. So we make use of the theorem 1. This is theorem 1. Theorem says a bounded monotonic function is of bounded variation. So that means if you can show that this function is monotonic, then we are there. And it's monotonic since f of 0 is sine 0, which is 0. F of pi over 2 is sine pi over 2, which is 1. So you now see that f of 0 is less than or equal to sine s is less than or equal to 1. Therefore, f of s is equal to sine s is monotonic. Hence, f is of bounded variation. So the question now says you find the total variation. So remember, when we were in the course of proving the theorem, this is the theorem. In the course of proving it, we later found out that this total variation is same thing as f of b minus f of a if a function is bounded and monotonic. So what they ask us to find, which is f of 0 to pi over 2, will just be f of pi over 2 minus f of 0. This is sine pi over 2 minus sine 0. And sine pi over 2 is 1. Sine 0 is 0. So this is 1. So that is the total variation is 1. And this one shows that it is of bounded variation. Have a nice day.